Hello friends, welcome back. In this video lecture, I will explain the chapter number 9, Light, Reflection and Refraction from the subject Science, class 10, CBSE board. We see variety of objects around us. However, we are unable to see anything in dark room. When lighting up, we can see the object. During daytime, due to sunlight, we are able to see the object. Why it is? Because when light falls on any object, it gets reflected, and the reflected light reach to our eyes, and we are able to see the things. Again, through transparent medium, why we are able to see? Because light passes through the transparent medium. So there are n number of wonderful phenomena associated with light, such as image formation by mirror, twinkling of star, beautiful colors of rainbow, bending of light by medium. From all these phenomena, what we see or what we conclude? We conclude that light seems to travel in straight line path. Now, I will explain through experiment. Take the torch, fall its light on small opaque object nearer to it, nearer to torch. It will cast its shadow. It will not pass through, light will not pass through the opaque object. It will cast its shadow, clear and distinct shadow. So this conclude that light seems to travel in straight line path, and we can represent it by ray of light, or we can call this as ray of light passing. In this chapter we will study phenomena of reflection, refraction of light using the straight line propagation of light. Thank you for watching the video. If you like it, please do share it and subscribe channel for more such fruitful videos. Thank you. Hello friends, welcome to my channel. In this video, I will explain the phenomenon of reflection of light by plane mirror. First, we'll understand what is meant by mirror. Mirror is a piece of glass which has two surfaces. One surface is reflecting surface and backside surface is non-reflecting surface. When reflecting surface is plane, highly polished, then this mirror is called as plane mirror. And when a light or ray of light falls on the plane mirror, it falls on a single point, this point. This is the ray of light, that is incident ray. This ray is called as incident ray. It falls on the mirror at point this point is called point of incidence. This line is normal to the mirror, that is this line makes an angle of 90 degree with the mirror at point of incidence. When ray falls, it gets reflected. This reflected ray is called, this ray is called reflected ray. The angle between incident ray and normal, this angle is called angle of incidence. The angle between normal and reflected ray, this angle is called angle of reflection. Now, there are two laws of reflection. First law, the angle of incidence is always equal to angle of reflection. Second law, the incident ray, the reflected ray and the normal to the mirror at point incidence, they all lie in same plane. Now see another figure for reflection of light by plane mirror. Now, most important point to memorize. Image formed by the plane mirror is always virtual and erect. Erect means straight. The size of the image is equal to that of the size of object. The image form is far behind the mirror as the object is in front of it. Whatever object distance in front of mirror, at same distance image will be formed inside the mirror. And again one more point, the image is laterally inverted. The image formed by plane mirror is laterally inverted. Thank you for watching the video. If you like, please share it and subscribe channel for more such fruitful videos. In the next video, we will learn about the spherical mirrors. You can call me for home tuition also. The contact details are shown on the screen. If you have a group of 3 to 4 students at your place, I will take tuition for them, for that group of students, 3 to 4 students at your place. Thank you. Hello friends, welcome to my channel. In this video, I will explain about the spherical mirrors. Already we have discussed what is meant by mirror. Already you know, mirror is a piece of glass which has two surfaces. One surface is reflecting surface, another surface is non-reflecting surface. Here two images are shown on the screen. This is the first image, this is the second image. In this is the mirror. So it has two surfaces. One surface is this surface. This side surface is reflecting, and this side surface is non-reflecting. Same way for this mirror also, this surface is reflecting surface and this surface is non-reflecting surface. Now, in reflecting spherical mirror, spherical means part of sphere. These mirrors are made up of part of sphere, means they are curved. These mirrors are curved. Curved means spherical, part of sphere. When reflecting surface is curved inward, reflecting surface is curved inward, this type of mirror is called concave mirror. Again, when reflecting surface of the mirror is curved, this is curved surface, curved outward, this is curved outward, then such type of mirror is called convex mirror. Yes, this is about the spherical mirror. Now, hello friends, welcome back. In this video, I will explain terminology of spherical mirrors. There are some terms which are required to be understood when we study spherical mirror concept. These terms are pole, curvature of center of curvature, radius of curvature, principal axis. Now, this is the theoretical part. There are definitions and anything. Now, we'll see in image or in figure. First figure is concave mirror. Second figure is convex mirror. This point P is called pole. It is the center of mirror. It is the center of mirror. It is the center of mirror and it lies on the mirror itself. Now, as you know, this is the mirror is spherical. So it forms sphere like this. It forms sphere like this. It form sphere, complete sphere like this, or it form complete sphere like this, because this mirror, spherical mirror, is part of sphere. So now, if it is sphere, it has to be a center. This center is called center of curvature. Here, center of curvature. Now, distance CP, as C, P point is on mirror, C point is a center, then CP is radius and we call it as radius of curvature. Radius of curvature. Here CP, distance radius of curvature. Now, here ray diagrams are shown. This parallel ray falls on the mirror, it gets reflected. This ray falls on the mirror, get reflected. This ray falls on the mirror, get reflected. This ray falls on the mirror, get reflected. This all rays falls on the mirror and get reflected. After reflection, these ray meet at a point. These ray meet at a point. This point is called focus. This point is called focus of mirror. Same way, same terminology will be here. Now, see the difference in concave mirror and convex mirror. Ray, incident ray, falls on the mirror. After reflection, rays are converging at single point. Rays are converging. So, concave mirrors are convergent mirrors. Here, when ray falls, it gets reflected. This ray get reflected. This ray get reflected. This ray get reflected. So after reflection, these rays diverges. So we can say convex lens is divergent nature. Next point. Point of difference. See, center of curvature focus is on same side, that is reflecting surface side. Center of curvature focus, they are on same side of reflecting surface. This is observed in case of concave mirror. But see, in case of convex mirror, focus, center of curvature are on non-reflecting side of mirror. They are on non-reflecting side of mirror. Yes? Now, one thing is remaining. A line CP perpendicular at P a line CP. If it extends, if we extend this line CP on both the side, and this line is perpendicular to mirror at point P, this line is called principal axis. This line is called principal axis. Now, one more term, MN, distance MN. You can measure vertical distance MN. This is M is this point, N is this point. This point is M, this point is N. If we join it vertically and measure the distance, this distance is called aperture. This distance is called aperture. This is what related with terminology of spherical mirror. If you like the video, please do share it. Subscribe the channel for more such fruitful videos. If you can call me for home tuition as well. I am taking home tuition for subject mathematics, science and SST. Thank you. Hello friends, welcome back. In this video, we will see a concept of focal length for two different types of mirrors, that is concave mirror, convex mirror. Figure A shows concave mirror, rays are falling on the concave mirror. After reflecting, ray converge at point F. This F point lies on principal axis in between center of curvature and pole. This point is called focus. Already you know. Same phenomena for convex mirror. F is the focus of that convex mirror. It lies on the principal axis in between center of curvature and pole. Pole is represented by capital P. Focus or principal focus is represented by capital F. Center of curvature represented by C. Radius of curvature represented by capital R. And now the distance FP is called focal length of that spherical mirror. The distance FP is called focal length of that spherical mirror, and focal length, it is a distance and it is represented by small f. It is represented by small f. Same way, distance FP is represented by small f and it is focal length of that mirror. Now, there is a relation between radius of curvature and focal length. What is the relation? Radius of curvature R is equal to 2 times focal length. Radius of curvature of any spherical mirror is equal to 2 times its focal length. Again, listen. Radius of curvature of any mirror, spherical mirror, is equal to twice the focal length of that spherical mirror. Thank you. Hello friends, welcome back. In this video, I will explain image formation by spherical mirror. As you observed in earlier figures, when number of rays falling on mirror reflecting surface of mirror, and it will get reflected back. But to know how image is formed, we require only two rays. So which ray we have to select, that we will study first. And then based on the condition that where object is placed, where object is placed, we will see find the nature, position and size of image form for that condition. So here for concave lens you have 6 position where we can place the object. This position of the object is given. We have to find out this. We have to find out this. So 1, 2, 3, 4, 5, 6 positions are of objects are possible for concave mirror. And two positions are possible for convex mirror for object placing. Now see here number of rays coming, already I have said, but we have to select only two rays to know the nature of image or size of image, or to find the position of image. So here 4 rays are given. Out of this 4 ray, you have to consider only 2 rays. Yes. So first ray, a ray parallel to the principal axis. Second ray, a ray passing through the principal focus of a concave mirror, or a ray which is directed towards the principal focus of convex mirror. Ray number 3, a ray passing through the center of curvature of concave mirror or directed in the direction of center of curvature of convex mirror. And fourth ray, a ray incident obliquely to the principal axis towards point P, that is pole of the mirror, for both the mirror. Out of this four ray, you have to select only 2 rays, because you already know when a ray fall on the mirror, how it will get reflected. So see this table. First ray, ray selected, a ray parallel to the principal axis. After reflection, it will pass through the principal focus in case of concave mirror, or appear to diverge from the principal focus in case of convex mirror. So see figure for this condition. A ray parallel to the principal axis falls on the mirror, concave mirror. It will get reflected and passes through the focus of that mirror. Here, as far as convex lens is concerned, ray parallel ray fall on the mirror, convex mirror. It will get reflected. When we extend this ray back, it will direct passes through the point F, that is focus. So you know, when ray is parallel to the principal axis, falls on mirror, it gets reflected and passes through the, after reflection, it passes to the principal focus. That is the first ray. You know ray, type of ray, before reflection, that is incidence, and after reflection, what is its nature, that you know. Now second ray, a ray passing through the principal focus of concave mirror, or ray which is directed towards the principal focus of convex mirror. After reflection, it will emerge parallel to the principal axis. A ray passing through principal focus, incident on mirror, concave mirror, it will get reflected as a parallel ray, or it is parallel after reflection, it is parallel to the principal axis. Same way, a ray come and incident on convex mirror. When we extend this ray, dotted means we have extend this ray, so it appears to be pass on principal focus. When it gets reflected, it will be parallel to the principal axis. Two rays, you know ray after reflection, you know its nature. Now third ray, a ray passing through the center of curvature of a concave mirror, or directed in the direction of center of curvature of convex mirror. After reflection, it is reflected back along the same path. Means a ray which is passing through center of curvature falls on the mirror, it will get back reflected in the same way. Same path it will get reflected. So the ray, this ray incidents on convex lens, it's appear to be passing through center of curvature, it will get reflected back. Then fourth ray, a ray incident obliquely to the principal axis. Oblique means it has some angle to the principal axis. Oblique means ray makes some angle with horizontal line. But here horizontal line is principal axis. Obliquely to the ray incident obliquely to the principal axis, and incidence, point of incidence is P. Point of incidence is P. It will get back reflected same like this. So the knowing the nature of this type 4 rays, you can select any 2 rays for all 6 conditions, or 6 conditions for concave mirror, 2 conditions for convex mirror. So now, and see here, in these cases, laws of reflections are followed. You know what are the laws of reflections? All laws of reflections are followed. Now, if you know this 4 rays, how it behaves after reflection, because keep in mind one thing, image is formed where rays after reflection meets. On the same point, image is formed. After reflection, the reflected ray meet at single point. So that shows position of image. Now see the conditions. Image formation by concave mirror. First condition, object is placed at infinity. When we place object at infinity, rays coming rays coming from the object, they are parallel. So when parallel ray falls on mirror, concave mirror, it get reflected and passing through point F, focus. This parallel ray get reflected and passing through point focus. After reflection, these two rays meet at point F. Here the image is formed. Image, see, image is diminished. Image is point size. Image is point size. See, image is point size. See, at infinity, position of the image, at focus, size of image, point size, nature of image, real and inverted. That I will tell you when to take nature, real and inverted, and when to take nature, virtual and erect. Now, second condition. Second condition, object is placed far beyond the center of curvature. Far beyond the center of curvature. This is the object AB. First ray taken parallel, it ray incidents on mirror and get back reflected. We know the nature of parallel ray. When parallel ray falls on the mirror, it gets reflected and after reflection it passes through the point F. Now take one more ray. We require two rays. So second ray passing through the center of curvature. Second ray center of curvature, it gets back in the same path. It get back reflected in same path. So these two ray after reflection meet at point A dash. So A dash B dash is the image formed. So now see position of image. Where image is formed? In between C and F. The image is formed in between C and F. This is position. Now nature. Nature of image, it's real and inverted. See, this image is like this object is like this, image is like this. Nature is real and inverted. When real and inverted. And image is size of image. Image is smaller than object. Image is smaller than object. Now, third condition. Object is placed on center of curvature. You placed object at center of curvature. Now take one ray parallel. It will get reflected and passing through the point F. You know, second ray you selected is ray passing through the focus. And what is the nature after reflection? It gets reflected and it will be parallel to the principal axis. So after reflection, two rays meet at point A dash. B dash, A dash is the image form. Now see, image is formed at center of curvature itself. The position of image at center of curvature. size of image same as the object, same as the object, and nature of image real and inverted, real and inverted. Now condition 4, object is placed in between center of curvature and focus. Object is placed in between center of curvature and focus. Now first ray, select parallel ray. After reflection, it passes through the point, through focus, extended. Now select second ray. Second ray is a ray passing through the center of curvature. When ray passing through the center of curvature falls on the mirror, it will get back reflected with the same path. These two rays after reflection meet at point A dash. A dash B dash is the image formed. Now see, image is formed far beyond C. Image is formed far beyond C. This is the position. Now size of image. Size of image is larger than object. Size of image larger than object. Correct? Now image is real and inverted. Image is real and inverted. Now condition number 5. Image placed at focus. Object placed at focus. A, B as the object placed at focus. Take first ray parallel to principal axis. After reflection, it passes to the point F. Extend it. Take another ray passing through the center of curvature, falls on the mirror. After reflection, it will get back reflected with the same path. See, after reflection, these two rays are parallel. Parallel means they never meet each other. So image is formed at infinity. Image is formed at infinity. Nature of image is, if image is formed at infinity, nature is enlarged. Nature is enlarged. Or we can say image not formed. Image not formed. Image not formed. Yes. Now condition 6. The object is placed in between focus and pole. Object is placed in between focus and plane. This condition is given. Now take one ray, oblique ray from A, falls obliquely at P, it get back reflected obliquely like this. Second ray, take ray passing through the center of curvature, when falls on the mirror, get back reflected in the same path. See, this ray, if we extend this ray and this ray never meet here, so what we'll do, we extend this ray backward. We extend this ray backward, and after extending they meet at point A dash. So A dash B dash is the image formed. Now see, where image is formed? Image is formed behind the mirror. Behind the mirror. Then nature of image is, it is virtual. Why it is dotted? It is virtual. It is behind the mirror. Behind the mirror means it is virtual. And erect. Erect means straight. And nature is virtual and erect. And size. Size is larger than object. Larger than object, or we can say enlarged. Image size is enlarged. And now, have you observed anything here in these 6 cases? When image is formed on reflecting surface side, when image is formed on reflecting surface side, this is reflecting surface, image is formed on reflecting surface side, it is real and inverted. And when image is formed on non-reflecting surface side, when image is formed on non-reflecting side, this image is virtual and erect. This is the difference. You keep in mind, when image is formed on reflecting surface side, it is real and inverted. When image is formed on non-reflecting surface side, it is virtual and erect. Virtual and erect. Now, uses of concave mirror. So, based on the image formation, you understood the uses. Concave mirrors are commonly used in torch, searchlight, and vehicle headlight. Vehicle headlight to get powerful parallel beam of light. They are often used as shaving mirrors to see a larger image of the face. The dentist used the concave mirror to see large images of teeth of patient. Large concave mirror are used to concentrate sunlight to produce heat in solar furnace. So these are the uses of concave mirror. Now we'll see image formation by convex mirror. So this topic will somewhat easier. Now it has 2 cases only. It has 2 cases only. One case, this position of object. As far as convex mirror is concerned, only 2 cases. At infinity, object is placed, or position of object is at infinity, and between infinity and the pole. Between infinity and the pole. So first, and nature of rays, or which ray you have to select. You require at least 2 rays to decide the nature, size, position of the image. So which 2 rays you have to select? Whatever 4 rays given already. Out of these 4 rays, ray number 1, ray number 2, ray number 3, and ray number 4. You have to select any 2 rays out of these 4. Now case 1. Object is placed at infinity. The ray parallel comes, get reflected, parallel come rays, get reflected. These are divergent rays. Nature of the mirror is divergent. So extend rays backward, rays meet at point F. So image formed at point F. So what you know, when image is formed on non-reflecting surface side, it is virtual and erect. It is virtual and erect. It is point sized and it is formed at the focus. And it is formed at the focus. Now, second condition, when the object is placed at finite distance from the pole, from pole, finite distance, object AB, then first ray taken parallel ray, after reflection it will get reflected like this, extend this ray backward passing through the focus, because parallel ray when reflect, after reflection it will get passing through the focus, or as far as convex mirror is concerned, it appears to be passing through focus, we are extending back. Now, second ray, consider second ray which is passing through the center of curvature. When ray passing through center of curvature, it will get back reflected in same path. Now, after reflection, these two rays meet at point A dash. So, B dash, A dash is the image. A dash B dash is the image of object AB. See, the object image is formed in between pole and focus. Image is formed in between pole and focus. Image size is smaller than object. Smaller than object. And nature of image is virtual and erect, because it is formed on non-reflecting surface side. Now this virtual and erect. Now most important thing, a real image is formed when rays converge, whereas virtual image occurs when rays only appear to diverge. A real image is formed when rays converge, and virtual images occurs when ray diverge. Or simply we can write, you can see, when image is formed on reflecting surface side, image is real and inverted, and when image is formed on non-reflecting surface side, it is virtual and erect. Now, this is the difference between real image and virtual image. So, point of difference. First, for real image is inverted. Virtual images are erect. Real image is always formed by convex lens. Virtual images can be formed by concave as well as convex or plane mirrors. Keep in mind, whatever images formed by the concave mirror, plane mirror, or some cases convex mirror are virtual in nature. Real images are formed on the screen. Virtual images appears to be on the lens or the mirror itself or back side of the mirror. Real images are always formed by concave mirror. Convex mirror forms virtual images. Real images are formed due to actual intersection of light rays. Virtual images are formed due to the imaginary intersection of light rays. Because see, for virtual images, this ray come, falls on mirror, get back, get reflected, and we have taken some extended these rays backward, and then only we got this point of intersection. That's why virtual images are formed due to the imaginary intersection of light rays. Now, uses of convex mirror. In convex mirror, real images are formed So it is used as a for rear view mirror in vehicles, because these mirrors are fitted on the sides of the vehicle, enabling the driver to see the traffic behind him or her to facilitate safe driving. Convex mirror are preferred because they always give erect image, though diminished image, but image is erect. So that is the most important point. That's why they are used in the rear view mirror in vehicle as well as side mirror for vehicle, because they give erect images. Also they have wider field of view as they are curved outward. See, convex mirrors are curved outward. Already we have learned in definition of convex mirror. Now, because of this, convex mirror enables the driver to view much larger area than would be possible with plane mirror. So that's why these are used in vehicle for side mirrors as well as rear view mirrors. This is all about the image formation by spherical mirror. So thank you for watching the video. If you like it, please do share it and subscribe the channel for more such fruitful videos. You can call me for home tuition also. I am taking home tuition for the subject mathematics, science and SST from standard 6 to standard 12. The details are shown, or contact details are shown on the screen. If you have a group of 3 to 4 students at your place, I will take tuition at your place for that group of 3 to 4 students. Thank you. Hello friends, welcome back. In this video, I will explain new Cartesian sign convention for spherical mirrors. You see some figure drawn on screen. This is the mirror. This side of mirror is left hand side. This side of mirror is right hand side. Now this side is reflecting surface side. This side is non-reflecting surface side. This P is the pole of the mirror and it is taken as origin. The principal axis x dash is taken as x axis. Horizontal distances are measured from point P, that is every time we are measuring distance from the origin, so measuring from P towards right, towards left or towards right. Vertical distances are measured from the principal axis upwards or downwards. First, object is always placed on the left side of the mirror, that is reflecting surface side. Then this is the direction of incident ray. The horizontal distances measured from P towards left, they are taken as negative. The horizontal distances measured from P towards right, it is taken as positive. The vertical distances measured from principal axis upward, taken as positive. The vertical distances measured downward from the principal axis, they are taken as negative. All this is about the new Cartesian sign convention for spherical mirror. So here whatever I have explained, that is written here, and same thing was written here, that is pole as taken as origin, principal axis taken as x axis, and distance are measured. So this is all about the new Cartesian sign convention for spherical mirrors. Thank you. Hello friends, welcome back. In this video, I will explain mirror formula and magnification. Mirror formula and magnification, these are the theoretical concepts. It has different quantities and relationship between quantities. So first quantity is object distance denoted by small u, image distance denoted by small v, focal length denoted by f, and relation between them in terms of formula, and this formula is mirror formula. So in spherical mirror, the horizontal distance of the object from its pole is called object distance. What is? It is represented by small letter u. Thus, distance or horizontal distance of the image from the pole of the mirror is called image distance, and it is denoted by small v. And already you know the distance of the principal focus from the pole is called focal length. And the relationship between these three quantities v, u and f is this: 1 upon v plus 1 upon u is equal to 1 upon f, or 1 divided by v plus 1 divided by u is equal to 1 divided by f. And this formula is called mirror formula. Next concept is magnification. Magnification, in simple term, magnification means zoom in, zoom out. Magnification produced by spherical mirror gives the relative extent to which the image of an object is magnified with respect to the object size. Means whether it is enlarged or whether it is smaller, that is nothing but magnification. Magnification is represented by m, small letter m. It has formula. Now, suppose height of image is h dash. Height of image is h dash, and height of object is h. Height of object is h. Then magnification m is represented by ratio of height of the image to the height of the object. Therefore, we can write m is equal to h dash upon h. Correct? Now, we write magnification in terms of image distance and object distance. Here, in this formula, we have written value of magnification in terms of ratio of height of image to the height of object. Now, magnification m is equal to height of image upon height of object, which is equal to minus v divided by u. Here minus sign is already in the formula. V image distance, u object distance, and whenever you are solving the numericals based on the mirror formula or magnification, use proper Cartesian sign convention, whatever you have learned earlier in this chapter. Now, see the sign convention. Here also, one more time I have explained. The height of the object is taken to be positive, as object is usually placed above the principal axis. The height of image should be taken as positive for virtual images. However, it is taken as negative for real images because real images are formed below the principal axis and virtual images are formed above the principal axis. That's why this sign convention is. Now, a negative sign in the value of magnification indicates that the image is real. If you solve any problem and find out the value of magnification, if value comes to be negative, what is its meaning? Its meaning is image is real. And if positive sign in the magnification, if you find out magnification value and it comes out to be positive, then what you say for this? Your observation will be real image is virtual. Negative sign in magnification indicates image is real. Positive sign in magnification indicates image is virtual. So all this is about the mirror formula and magnification. Thank you for watching the video. If you like it, please do share it and subscribe the channel for more such fruitful videos. You can call me for home tuition also, as well as if you have group of 3 to 4 students at your place, I will take tuition at your place for that group of 3 to 4 students. I am taking tuition for the classes standard 6 to standard 12, all boards, SSC, CBSE, ICSC, IB and all other boards, and subjects I am taking are maths, science, in science, physics, chemistry, biology, all the three plus SST. Thank you. Hello friends, welcome back. In this video, I will explain phenomena of refraction of light. Already you have studied the phenomena of reflection of light. When ray of light travels from one medium to another medium, it changes its direction of travel. This phenomena is known as refraction of light. To study refraction of light, you require two mediums. Both the two mediums are transparent, and we assume that light seems to travel along straight line path in transparent medium. Now we will study this phenomena by using this concept: refraction through rectangular glass slab. Means a ray of light traveling in air passes through the glass slab and then again from glass slab to air. So it will change the direction because medium changes. Firstly, it is in air medium. This medium is called as rarer medium. Why it is called a rarer medium? Because it has more space between the particles of air. Glass medium is called as denser medium. It is solid, and in solid, closely packed particles are there to make the material of solid. So the speed of light is more in rarer medium than solid. Now here this medium is air medium, and this rectangle ABDC is the glass medium. We follow all the laws of refraction or reflection here, and laws of reflection are same applicable for refraction phenomena also. Now this medium is air medium, this medium is glass medium. This ray EO is the incident ray. O dash, ray O dash is the refracted ray. Ray O dash H, ray O dash H is the emergent ray. Now incident ray EO, or we can say EF, is also incident ray, falls at point O. O is a point of incidence, or O is a change point where ray changes from air medium to glass medium. This N dash, this dotted line is a normal. Now this angle is angle of incidence for this ray I1. Then when ray O dash get refracted, it moves slightly towards the normal. It moves slightly towards the normal like this, and this makes angle with normal. This is the angle of refraction R1. Then it travels in a straight line path in glass medium. Now at O dash, the point again, O dash is the point of incidence, and O dash is the point of incidence where ray changes from denser medium or glass medium to air medium. So O dash H, ray O dash H or ray GH is the emergent ray, and it moves slightly away from the normal. This is the M dash is the normal, and ray moves away from the normal and moves further. If we draw this incident ray EF, if we draw like this, so this OP, line OP, it is imaginary line we have drawn. Then this ray or this line is parallel to this ray. This line is parallel to this ray. Means this ray and incident ray and emergent ray are parallel to each other, but they have some distance between them. O dash L. O dash L is the distance between them. Now, see why it is incident ray and emergent ray are parallel, because they are in same medium. Here also medium is air. Here is also medium is air. So that's why this ray EF or EO, incident ray, and emergent ray O dash H or GH are parallel to each other. Now this angle I2, the angle of incidence for this refracted ray at normal, to the normal at point O dash. R2 is the angle of refraction for ray O dash H with normal m dash. Now here at point O, when light travels from rarer medium to denser medium, ray is closer to or deviated towards normal. Deviated towards normal. This is because the speed of light is more in air medium and it is less in glass medium. That's why this happens. This refracted ray is diverted towards or deviated towards normal. Now, here at point O dash, ray is traveling from denser medium to rarer medium. And the speed of light is more in denser medium. So, ray deviates away from the normal. Ray deviates away from the normal. And because of this, incident ray and emergent ray are parallel. This is second reason why these are parallel to each other. And now, angle of incidence I1 is always equal to angle of incidence I2. Angle of refraction R1 is always equal to angle of refraction R2. And this is the phenomenon of refraction of light through rectangular glass slab. And see how ray or ray of light behaves when travels from one medium to another medium. Its deviation is towards normal or away from the normal is based on the speed of light in that respective medium. If you like the video, please do share it and subscribe channel for more such fruitful videos. And you can call me for home tuition also. The contact details are shown on the screen at the start of video or at the end of video. I will take tuition for the subjects mathematics, science, SST for the classes 6 to 12 for all the boards CBSE, SSC, HSC, ICSC, IGCSE, IB and all other boards. If you have group of 3 to 4 students at your place, so I will take home tuition at your place for this group of 3 to 4 students. Thank you. In the next video, we will study next phenomena of related with the light. Thank you. Hello friends, welcome back. In this video, I will explain laws of refraction. As you know, refraction is due to change in the speed of light. Why change in speed of light occurs? Because when light travels from one transparent medium to another transparent medium, it changes its speed of travel. Now, if we do some experimentation, the refraction of light have certain laws. First law, the incident ray, the refracted ray and the normal to the interface of two transparent media at the point of incidence all lie in the same plane. Second law of refraction of light. The ratio of sine of angle of incidence to the sine of angle of refraction is constant for the light of given color and for the given pair of media. This law is also known as Snell's law of refraction, and this law is true for angle of incidence I is greater than 0 and less than 90 degree. As you know, I is the angle of incidence, small r is the angle of refraction, then ratio of, this is trigonometric ratio, sine of angle of incidence divided by sine of angle of refraction is equal to constant, and this constant is called refractive index of second medium with respect to first medium. This constant is called the refractive index of second medium with respect to first. And these are the two laws of refraction. Again, I am repeating. First law, the incident ray, the refracted ray, and the normal to the interface of the two transparent media at the point of incidence all lie in the same plane. Already we have seen this in earlier figure. Second law, the ratio of sine of angle of incidence to the sine of angle of refraction is constant for the light of given color and for the given pair of media. See here, pair of media. Here two media should be there. Two transparent media should be there. Then only refraction phenomena occurs. And this law is known as Snell's law of refraction, and it is true for angle of incidence greater than 0 and less than 90 degree. And this is expression form or equation form we are writing, and this constant is called as refractive index of second medium with respect to first medium. Thank you for watching the video. If you like it, please do share it and subscribe channel for more such fruitful videos. Thank you. Hello friends, welcome back. In this video, I will explain the phenomenon of refractive index. So already you have studied refraction phenomenon. Now, here we are considering two medium. When ray or ray of light changes medium of traveling, it gets refracted. And at how much amount it will deviate from the normal with respect to other. That is the concept of refractive index. Here medium 1 is air medium. We can call him rarer medium. Rarer medium means speed of light is more. Because in air medium distance between the particle is more. Second medium is glass medium. It is denser medium because closely packed molecules are there for medium 2. That is denser medium. Now, a ray of light AO traveling from air medium, that is medium 1 into medium 2, it get refracted. This ray OA is incident ray. Ray OB is refracted ray. N dash is a normal at point O. I is the angle of incidence. R is the angle of refraction. Now, let V1 be the speed of light in medium 1. V2 the speed of light in medium 2. Now, refractive index of medium 2 with respect to medium 1 is given by the ratio of the speed of light in medium 1 and the speed of light in medium 2. Now, symbolic representation is n to 1. N to 1. Now, we are writing or denoting refractive index by letter small n, and here suffix we are writing medium. First, the medium for which we are finding out refractive index, and second is the medium with reference to which we are finding out the refractive index. So now, in mathematical form or equation form, how to express refractive index? Now, refractive index n 21, it's not n21, n 21, refractive index of medium 2 with respect to refractive index of medium 1 is equal to ratio of speed of light in medium 1 divided by speed of light in medium 2, which is equal to V1 by V2. So N21, see the for which medium we are calculating refractive index, that you write first, and here you write that speed of light in that medium in denominator place, and here you write the medium with reference to which we are calculating refractive index, and the speed of light in that medium you write at the numerator. Means a reference medium is at top and the medium for which we are finding out refractive index, right, denominator. Now, if we are finding out refractive index of medium 1 with respect to 2, so refractive index of medium 1 with respect to 2, so 2 here, speed of light in medium 2 divided by speed of light in medium 1, so 2 here, 1 here, V2 by V1. Now, if medium 1 is vacuum or air, then refractive index of medium 2 is considered with respect to vacuum or air, and this is called the absolute refractive index of the medium, and it is simply written as N2. Now, if C is the speed of light in air and V is the speed of light in medium, then the refractive index of medium is given by Nm is equal to speed of light in air divided by speed of light in the medium, which is equal to C divided by V. Means if we take a reference medium is vacuum or air, that time here we are not mentioning that. We are just mentioning the medium for which we have to find out refractive index. Now, in this table, I have listed some material with their absolute refractive index. So again, what is meant by absolute refractive index? It is the refractive index of material with respect to air or vacuum. Because speed of light is more in air or vacuum. So this is all about the refractive index of if two mediums are considered and absolute refractive index. If you like the video, please do share it and subscribe channel for more such fruitful videos. And you can call me for home tuition also. All the contact details are shown on the screen at the start of the video. I am taking home tuitions for the subjects mathematics, science and SST for classes 6 to 12 for all the boards. The classes are available or home tuitions are available online as well as offline. Thank you. Hello friends, welcome back. In this video, we will study more about convex lens and concave lens and their terminology, and one more concept of focal length. Now, in figure A, you are seeing convex lens. O is optical center. This F1 is focus 1, F2 is focus 2, 2F1, this distance OF1, same distance is 2F1, 3F1 like graph. Then C1 is the center of curvature 1. This point is same as C1. This point is center of curvature 2, C2. This imaginary line C1, C2 passing through O is called principal axis. Same terminology is for concave lens. In figure B, concave lens is there. Same terminology is there. Now, both the two lenses have two focuses, or you can call them as two foci. Lens are having two foci. Now, see carefully figure A. Several rays of light parallel to the principal axis falls on the mirror, falls on the lens, convex lens. After refraction, they get converged at point F2. So F2 is called as principal focus of lens, and the distance of point principal focus from the optical center measured horizontally is called as focal length of that lens. Now, as per sign convention, new Cartesian sign convention, focal length of convex lens is positive because it is measured on right hand side. Now, when parallel rays or rays of light parallel to the principal axis falls on concave mirror, after refraction they get diverged. When we draw this refracted ray backward, they meet at point f1. So f1 is the principal focus for concave mirror, concave lens. And see, the distance measured horizontally from optical center to point f1, that is up to principal focus, it's called as focal length of that lens. So here OF1, this distance is focal length for this concave lens. Now, as per sign convention, focal length of concave lens is negative. Focal length of concave lens is negative. Thank you for watching the video. If you like it, please do share and subscribe channel for more such fruitful videos. In the next video, we will see another phenomena related with the lenses from this chapter. Thank you. Hello friends, welcome back. In this video, I will explain refraction by spherical lenses. First, we'll study what is meant by lens, spherical lens, what is the terminology for spherical lens, and then we'll study refraction phenomena by these spherical lenses. So, starting with what is meant by lens. Any transparent material, if it is bounded by two surfaces, any transparent material bounded by two surfaces of which one or both surfaces are spherical, it forms a lens, or it is called as the lens. So what is the meaning? This means that lens is bounded by at least one spherical surface. In such lenses, the other surface would be plane. So as you know, lens should have two surfaces, out of which one surface is may be plane and one surface compulsorily spherical. Now, types of lenses. A lens having two spherical surfaces bulging outward. See figure A. A lens have two spherical surfaces bulging outward. Such a lens is called double convex lens. Such lens is called double convex lens, or simply it is called as convex lens. See figure A. Now, convex lenses are converging lenses. Convex lenses are converging lenses because after refraction, rays get converged. That's why convex lenses are converging lenses. Similarly, another type of lens, see the figure B, a double concave lens. This is figure B is double concave lens because this figure lens is bounded by two spherical surfaces which are curved inwards, and middle part is thinner than edges. Edges are thicker for concave lens. And see, This type of concave lens is called double concave lens, or simply you can call it as concave lens. Now, these lenses are divergent in nature. These lenses are called, or concave lenses are called, diverging lenses. Why? After refraction, these lenses or the rays diverges. After refraction, the rays diverges. That's why these concave lenses or these lenses are called diverging lenses. Now, terminology. A lens, either a convex lens or concave lens, has two spherical surfaces because two spherical mirrors are there to form the lenses. So, everything or both the lenses have two spherical surfaces. Now, if both two spherical surfaces, there are two center of curvatures. So it is denoted by C1, C2. As you know, principal axis, an imaginary straight line passing through the two centers of curvature of a lens and optical center. Optical center is the center of lens. Imaginary straight line passing through the two centers of curvature of lens and optical center is called principal axis. Optical center is represented by letter capital O. A ray of light through the optical center of a lens passes without showing any deviation. If ray of light passes through the optical center of lens, it will not show any deviation after refraction. Now, one more thing. The effective diameter of circular outline of spherical lens is called its aperture. Aperture is same whatever we have studied in case of mirrors. Now, here in this chapter, or as far as 10th standard is concerned, we will confine our discussion in this chapter to such a lens whose aperture is less than its radius of curvature. Second condition is two centers of curvature are equidistant from optical center. Such lenses are called thin lenses with small aperture. If aperture is less than radius of curvature and two centers of curvatures are equidistant from the optical center O, such lenses are called thin lenses with small aperture. Now see the figure. Everything is written. First figure is for convex lens. Second figure is for concave lens. Hello friends. In this video we will study as like spherical mirror to draw the ray diagram for image formation by lenses. Which type of rays we need to select. Here three rays are given. Out of these three rays, we have to select any two rays to study the drawing of image formation by lenses. First ray, a ray of light from the object parallel to the principal axis after refraction from a convex lens passes through the focus, principal focus on other side of the lens like this. In case of concave lens, the ray appears to diverge from the principal focus as located on same side of the lens like this. Second ray, a ray of light passing through principal focus after refraction from a convex lens will emerge parallel to the principal axis like this. A ray of light appearing to meet at the principal focus of concave lens after refraction will emerge parallel to the principal axis like this. Third, a ray of light passing through the optical center of a lens will emerge without any deviation like this. Then we'll study ray diagram for image formation by spherical lenses for different conditions. From these three rays, you have to select any two rays to study image formation by spherical lenses. Thank you. Hello friends, welcome back. In this video, I will explain image formation in convex lens for 6 different positions of object. For this, we'll study ray diagram. So as you know, to know the nature, position and size of image, we require at least two rays. Which two rays we need to select? Already we have studied. There are three rays. Based on these three rays, we have to select any two rays. So now position, and based on the position of object, we'll decide which ray we're going to select. Now, first case, when object is placed at infinity. When object is placed at infinity, the ray coming from the object are parallel to each other and parallel to principal axis. So ray coming from the object parallel to principal axis falls on the convex mirror. After refraction, they passes through the focus or principal focus of the mirror on other side. And as you know, convex lens is convergent nature. So all the rays, parallel rays passing through the principal focus on other side. So here image form is at the meeting point of emergent rays, or after refraction the rays meet each other, and the meeting point is the point where image is formed, and this is the position of image. So here position of image is at focus f2. Size, as you seen, size is point sized image and it is highly diminished, and its nature is real and inverted. Now second case or second position, object is placed beyond 2f1. Object is placed beyond 2f1. Here is object AB. First ray selected parallel to the principal axis. After refraction, it passes through the principal focus f2 on other side. Second ray selected, ray passing through the optical center, which will not show any diversion after refraction. So it will pass like this, and both these rays after refraction meet at point A dash. So B dash A dash is the image form. Now where is image form? Position of image is in between F2 and 2F2, in between F2 and 2F2. Relative size of image, it is diminished, it is diminished. And nature of the image, nature of the image is real and inverted, real and inverted. Now third case, object is placed at 2F1, object is placed at 2F1, first ray selected parallel to the principal axis, after refraction passes through the principal focus on other side, second ray selected, ray passing through the optical center, after refraction it will not show any diversion, it will go directly like this, and where these two rays meet after refraction, that is point A dash, and A dash B dash is the image. Now where is image formed? Image formed at 2F2. Image is formed at 2F2 position. Now relative size of image, size of image is same size as that of object, same size as that of object. And nature of image, nature of image real and inverted. Nature of image is real and inverted. Now case 4. In case 4, object is placed in between F1 and 2F1. Object is placed in between F1 and 2F1. Now two rays selected, first parallel ray, ray parallel to principal axis, after refraction it will pass through focus F2 on other side, and second ray selected, ray passing through the optical center, after refraction it will not show any diversion, it will go like this. So after refraction these two rays meet at point A dash, so this will be A dash, B dash is the image. So where is image formed? Image position is beyond 2F2, beyond 2F2, and image is, see the object, see the image, image is enlarged, and image is, nature of image, nature of image is real and inverted, real and inverted. Now case 5, object is placed at F1, focus F1, say two rays, first ray selected, ray parallel to the principal axis, after refraction it passes through the F2 and go like this, second ray selected, ray passing through the optical center, after refraction it will not show any deviation, it will go right like this. See these two rays after refraction they are parallel, parallel means they never meet each other, means image is formed at infinity. If image is formed at infinity means we couldn't find its nature and we can't see image, so image would not be formed, because these two rays after refraction they never meet, and our criteria is these ray, wherever these ray meet will get the image. But if these rays are not meeting means we are not getting any image, so image is not formed in this case. Now last case, if object is placed in between optical center and F1, object is placed in between optical center and focus F1. So first ray selected, parallel to the principal axis, after refraction it passes through the focus F2 on other side and it will go like this. Second ray selected, ray passing through the optical center, after refraction it will not show any diversion or it will go like this. So these two rays, if we clearly watch, closely watch these rays, they never meet. So for this, what we'll do, we draw rays backward side. So they meet at point A dash. When we draw these rays backward, these rays meet at point A dash. So A dash B dash is the image formed. Now position of image on the same side, of object, then image is enlarged, and now see the difference. Image is virtual and erect. Image is virtual and erect. So from these 6 different cases, that is position of the object, what you understood? When for convex lens, when image is formed on the other side of lens, it is real and inverted. And if image is formed on same side of lens, it is virtual and erect. So this is the difference. Now for after this, we will study image formation by concave lens for various positions of object. For concave lens, you have only 2 positions. First position, when object is placed at infinity. Object is placed at infinity. As you know, when object is placed at infinity, the rays coming from the object are parallel to the principal axis. So we have selected 2 rays, they are parallel to the principal axis. After refraction, each ray get diverted like this. These are the emergent ray also. When we draw backward these rays, they meet at focus F1 on same side. Now, so image is formed at this point. F1, focus F1, focus F1. Now image is highly diminished and it is point size. See, image is point size. And image is virtual and erect. As you know, as far as lens is concerned, if image is formed on the same side, it is virtual and erect. If image is formed on other side, it is real and inverted. Now second position of object. Object is placed between infinity and optical center. Object is placed between infinity and optical center. So like this. First ray selected, ray parallel to the principal axis. After refraction, it will go like this. And if we draw this ray backward, it will pass through the focus F1. Second ray selected, a ray passing through the optical center. It will not show any diversion or deviation after refraction. So these 2 rays meet at point A dash. So A dash B dash is the image formed. Now see, image is formed in between optical center and focus F1. Image is diminished. Image is smaller in size and This is the size and nature of the image is virtual and erect because it is formed on the same side of the lens. So this is all about the image formation by lenses for different positions of object and respective ray diagrams. In the next video, we will see further part. Thank you for watching the video. If you like it, please do share it and subscribe the channel for more such fruitful videos. You can call me for home tuition also. The contact details are shown on the screen at the start of the video. I am taking home tuition for the subjects mathematics, science and SST for classes 6 to 12, all the boards. If you have group of 3 to 4 students at your place, I will take tuition at your place for this group of 3 to 4 students. Thank you. Hello friends, welcome back. In this video, I will explain sign convention for lenses. We follow same sign convention whatever we have used for spherical mirror. Sign convention is applied for image distance, object distance, image height, object height, and they are taken from optical center in lens. All the distances, horizontal distances are taken from optical center. Now, according to the sign convention, the focal length of convex lens is positive and focal length of concave lens is negative. These are the point to remember. Now, take care of appropriate sign convention for values of U, V, F, object height and image height. U means object distance, V means image distance, F means focal length. Whenever in the numerical, if you are using these values, take care of sign convention. Now, for lens formula, like earlier in mirror, we have seen mirror formula and magnification. Magnification is same for mirror also and lens also, concept of magnification. Now lens formula. Lens formula gives the relationship between object distance represented by small u, image distance represented by small v, and focal length represented by f. And the lens formula is like this: 1 upon v minus 1 upon u is equal to 1 upon f. This minus sign is from formula. Whenever we put the values of v, u, f, take care of sign convention. Use sign convention and then put the values. Now, magnification. Magnification is same. Concept is zoom in, zoom out. At what extent image will be enlarged or smaller. That is nothing but magnification. And it is represented by small letter m. Let h be the object height and h dash be the image height. Now, magnification produced by lens is the ratio of height of image to the height of object. That is m is equal to h dash upon h. Now, this is the one formula. Another formula for magnification is ratio of image distance to the object distance. Magnification is equal to ratio of image distance to the object distance. So magnification m is equal to v divided by u. This is the second formula for magnification. Now you try to compare magnification formula for mirror as well as lens. Lens formula and mirror formula. Find out the differences and comment me the differences. Thank you for watching the video. If you like it, please do share it and subscribe the channel for more such fruitful videos. In the next video, we will see all the numericals from this chapter. You can call me for home tuition, or if you have group of 3 to 4 students at your place, I will take the tuition for this group of 3 to 4 students at your place. I am taking home tuition for the subjects mathematics, science and SST for the standards 6 to 12. All boards, that is CBSE, SSC, ICSC and IB, IGCSE and all other boards. Thank you. Welcome back. In this video, I will explain power of lens. Already you know what is meant by lens. Power of lens is defined as it is the degree of convergence or divergence of light rays achieved by lens. It is represented by letter P, capital P. There is a relationship between power and focal length F. The power of lens is reciprocal of its focal length. And this formula is written here. Power of any lens is reciprocal of its focal length. Now, for convex lens, power is positive. For concave lens, power is negative. These are the points to remember. Convex lens, power is positive. Convex lens, power is positive. Concave lens, power is negative. Now, the SI unit of power is dioptry. Power is dioptry and it is represented by capital D. Now, power is equal to 1D, which is equal to 1 meter raised to minus 1. So that is here power is in dioptry. 1D is equal to 1 focal length meter raised to minus 1, because see, meter raised to minus 1 is equal to 1 upon meter. So 1D is equal to 1 upon meter. So this formula achieved. Here I have put only units. Power unit is dioptry is equal to 1 divided by focal length unit is meter. 1D is equal to 1 upon m. And in term we can write 1D is equal to 1 into m raised to minus 1. So this is the case. Now, example, if power is plus 2 dioptry, we know power is equal to 1 upon f, raised 2 is equal to 1 upon f. Now, taking reciprocals of both the side, we can do any mathematical operation with equation. Taking reciprocals from both the side. So, reciprocal of 2 is 1 by 2. Reciprocal of 1 f is f. So 1 by 2 is 0.5 is equal to f. F is equal to plus 0.5. Focal length is positive. Power is positive, means lens is convex lens. Now this example is for concave lens. Power is minus 2.5 t. Power is minus, lens is concave. P is equal to 1 upon F, same formula. Put the values, minus 2.5 is equal to 1 upon F, minus 2.5. This is the decimal. Write in fraction form. Minus 25 by 10 is equal to 1 upon F. Taking reciprocals of both sides. Reciprocal of this is 10 divided by 25 is equal to reciprocal of 1 upon F is F. This minus sign as it is. So 5 2s are 10, 5 5s are 25. So 2 minus 2 divided by 5 is equal to F. If we divide 2 by 5, we'll get 0.40. Minus sign as it is. Minus 0.40 is equal to F. Therefore, F is equal to minus 0.40 meter. So that is the focal length. If power is given, you can calculate its focal length. And already you know power is reciprocal of its focal length. So if focal length is smaller, power is higher for that lens. And if focal length is larger, power is less for any lens. Thank you for watching the video. If you like it, please do share it and subscribe channel for more such fruitful videos. Thank you.